Good morning, everyone, and thank you for joining us today for the presentation New Module Technologies and Formats in Fall 2020, brought to you by AEE Solar. Before we begin, if you're experiencing any technical difficulties, please notify me by typing in your question in the question section of your control panel on the right side of your screen and click send. After the presentation, we will have a Q&A session. You're welcome to submit your question at any time during the webinar, and we'll do our best to answer as many as possible after the presentation. Any questions that we can't get to, we will follow up via email. So don't be shy, please send any of your questions in. Also, after the presentation, there will be a brief survey that will pop up in a new window immediately following the webinar. Please take a couple minutes to complete it, and we will email you a copy of the presentation. It's really helpful if you are able to give us any feedback that you have. We really do take it to heart, and we use it to help guide us to bring you topics that you're interested in for future webinars. So yeah, please participate in that survey. Meanwhile, I don't see any questions or issues coming through on the technical side. So if there are no questions, I would like to introduce our presenter today, our very own Josh Brister, Senior Manager of Product Management and Marketing for AEE Solar. Josh, I'm passing the presentation over to you.
Excellent. Thank you, Jamie, as always. And thanks to all our listeners out there across the country. Hope you guys are having a great Friday. You know, if nothing else, COVID has made me appreciate my Fridays more and more. So yeah, we're here to talk about new module technologies, how new tech and old physics are changing our industry. Excited to tell you more about that. And yeah, let's dig in here. So as always, like starting with an agenda, kind of lay out where we're going, what we plan on talking about. So to lead us off here, I'd like to talk about where we are and how we got here. So what's the prevailing module technology? How did we get here? A little bit about you know, how modules have evolved over the years. Most of what we're going to talk about today, though, is what's new. So some new module technologies like HJT. We'll talk a little bit about, you know, a somewhat new topic, and that's split cell technology. It's pretty widespread, pretty common at this point. Most of what we'll talk about, though, is going to be new wafer sizes, new formats on the horizon. We'll give you guys some points to consider. So, you know, above and beyond just the watt class number on the back of the data sheet, what are the things you got to keep in mind as you make some of these module decisions for your business? Takeaway. So, you know, I'd like to leave you guys with some food for thought here. Always encourage you guys to rely on quality. And we'll finish up with our product offer and our roadmap, basically what we've got and where we're going. So that said, let's dig in. Where are we? So, you know, what's common in the market? What's the prevailing technology? The prevailing technology right now is mono PERC wafers and cells. You might say that split cell mono PERC is maybe even a little more popular than the traditional mono PERC. N-type is out there as, you know, kind of a premium offer. On the right here, you've got a slide I like sharing, and this is from IPEV's study in 2017 on, 2019, on what to expect in the market and what the popular silicon material types are going to be over the next couple of years. And I like these slides because they, you know, they serve one as forecast for where we're going, and then it's always interesting to look back and see what the thoughts were on what we were going to have. Kind of like when you go to Disneyland and you tour around Tomorrowland and you realize, oh, that's what they thought the future was going to look like, and what an interesting contrast that paints. So in 2019, when this was published, you know, the prevailing types were still, in terms of just total volume, we're still multi-crystalline silicon. You know, obviously that's fading from the US market. We tend to skew more towards premium type product than maybe the rest of the world. P-type mono was really the bulk of the market this survey had predicted for 2020, with N-type coming in to kind of replace that as prevailing technology. And I'd say that's still the case. You know, this survey here didn't really differentiate too much between mono PERC and split cell mono PERC. I'd say P-type is still the prevailing wafer technology out in the market. In terms of prevailing dimensions, you know, we can haggle over fractions of an inch, but for the most part, 40 inches wide, somewhere around 66 inches tall, it's basically your common size. And yeah, there's some variations to that. Some of the LG Neon R products are a little longer. Some things are, you know, marginally narrower or wider, but for the most part, that's what we're seeing. You know, essentially a 2-to-1 aspect ratio. And that becomes important in designs and array layouts when you're looking at mixing landscape and portrait orientations. If you're trying to mix those into one array and make it look tidy, 2-to-1 aspect ratio really helps kind of organize into nice tidy blocks, and we'll see that later in the slide deck. So what's new? And this is where we talk about new technology and what I call the old physics. So some of the new technology, we've gone from mono to split cell now to heterojunction technology, HJT. So the theory behind moving to split cell was decreasing the current losses at each junction. So if your cells are smaller, they're going to have lower current. You've got more of them. You can reduce those parasitic losses and increase your overall wattage. So that's a bit of the new technology. The other piece here is increasing the number of bus bars. When you do that, you make the bus bars narrower, and you decrease the amount. You do two things. You decrease the amount of cell that's obstructed by each bus bar, and similar to split cell, you're increasing the number of junctions and decreasing the current loss at each junction. So that's the new technology. The kind of plain old physics that I mentioned is just a wafer size increase. So we'll speak to that in future slides. But basically, if you make the wafers larger and you make the module larger with the same technology, you will just plainly have more watts per module. And that's the what's the Montgomery Scott saying? You cannot change the laws of physics. Yeah, same technology, larger module, more watts. And then finally, just kind of organic increases in efficiency. And I say organic, and that's not to demean the work of all those smart scientists and engineers that work for module manufacturers. There's a lot of hard science that goes into this, but we've kind of come to take this for granted that every technology out there seems to eventually, those normal distribution curves of how a given module technology breaks up into different watt classes. Over time, they just start skewing to the right. So through technology and better processes and engineering, the same product line will eventually get more powerful, and then eventually they'll plateau and they'll kind of reach a theoretical limit for that technology. But we're still seeing that. So call that a mix of new technology and old physics. So this is split cell or half cut designs. We take what had previously been a 60 cell module. We cut each of those. We cut the module into two sections. We use half cut cells. So we take what had been a 156 millimeter or 161 millimeter cell. We split it in half, and we arrange all of those in this layout here. Doing that does a couple things. We're reducing the current in each cell by half, and remember remember from your engineering days or your handy cheat sheets that power loss is a function of current. So the loss in the module is reduced by a factor of 4 because the loss is equivalent to R times I squared. I is the current, so you get a big increase in, or I guess a decrease in losses by having the current. You also do a couple other things. but by splitting a module in half such as this, you increase the module's ability to handle shading. There are some trade-offs here, and that's that the junction boxes are in the center of the panel, and we've pretty much gotten through this as an industry, but there were some learning curve challenges associated with that on how to properly string your modules, how to do wire management. I won't dwell too much on this slide because, again, this is something that's been more or less prevailing technology for the last couple of years. Now, taking it one step further, it's kind of that old adage that if some is good, more is better. So heterojunction technology, and the leading example of this right now on the market is the Alpha series by REC Group. So what's happening here? Again, if we thought that increasing the number of cell junctions in split cell technology would reduce current losses, what would happen if we had just a substantially higher amount of junctions? So what REC's done here is taken a similar cell, a similar N-type cell, and instead of using bus bars with soldering technology, they've connected these cells to one another through a wire and film combination, and that's this upper layer here that you can see that almost looks kind of laminated onto this cell, and it basically wraps all the way around the cell. So these wires fuse to the cell to form connections at a much lower temperature. So without the soldering, there's no thermal stress. Greatly reduces the prevalence of hot spots on the cell, and you reduce the likelihood of there being weak points on that cell. And I don't have any good ultraviolet or thermal testing on these. That would be interesting to see, and I would imagine that you'd see some remarkable improvements from this technology. And then lastly, as I mentioned, by increasing the amount of cell connections between the wires and cell, you're improving the current flow. You're providing, some redundancy on those current flows, reducing the parasitic losses at each one, and the end result is higher wattage and increased efficiency in the same format. So going back to the beginning here, a good example of new technology. We'll talk a bit here now about kind of plain old physics, and that's wafer sizes. So a bit of a trip down memory lane, if you will. And I realize I've got a lorem ipsum typo here that I didn't clear, but harken back to the days of the early 70s when modules were hundreds of dollars per watt, and you had monocrystalline modules with cells that were around 100 millimeters in length, squared essentially. Well, we call them squared, but just about every module has dog-eared corners, just as a function of how the crystalline is grown in ingot form. In the early 2000s, we saw a little bit more standardization around a 125 millimeter wafer size. Fast forward to 2012, and the M0 format became popular. As a function of concentration of wafer manufacturing, there's fewer and fewer wafer fab manufacturers anymore, and they've become more and more consistent in wafer sizing. Some of this has to do with the technology behind how the silicon is grown. Call it more of it has to do with there's fewer manufacturers now, and each of them has become more standardized in what they do. 2014 saw a bit of a standardization around an M1, M2 wafer size. And the difference here between 156 and 156.75, pretty negligible. I would question if many of us actually saw this happening in the market, or if we just kind of took it for granted. Now here in 2020, and really what you're seeing is a lot more manufacturers focusing on an M6 cell, so 166 millimeters in length. And I don't have the diagonal dimensions here, but it's something that's pretty easily looked up. And this is really going to be the prevailing wafer and cell size moving forward. I didn't feature here some of the really large sizes, and we'll see that on the next slide, but if you pay attention to the news like I do, you've been bombarded by articles this summer about 550 watt commercial modules and 600 watt modules, and that's a function of increased wafer size and increased module size. So what do these look like? And pardon my boyish humor here, but size matters, frankly, when thinking about crystalline wafers. So we've got kind of and I borrowed this from Rena Technologies, who is a wafer manufacturing supplier. So you see here that, and these are scaled. You see here some of the differences between M0 from the early 2000s, M1, M2, you can call it 2012, M4 that's fairly popular now, and then M6. And I think you'd be hard pressed to to pull one of these out of the bin and be able to call what format it is. And I think the differences between 156 and 156.75 are negligible. The differences between that and 161 are a little bit more apparent. The jump to 166, though, side by side, you'd be able to spot that in a lineup. But remember back to your plain old physics, that in a square, the increase, it's a geometric function. You increase one side and you increase the area by a much larger factor. So the comparison here in this chart on the right is M0 versus M2. M2 saw a 1% increase in overall wafer area. From M0 to M6, that was 14%. So think about that. Just by increasing the, one of the side dimensions by 10 millimeters, basically the width of your pinky, you're able to increase that overall wafer size by 14%. And on the same technology, 14% increase in output. So size matters. It's an exponential function that drives a lot of output increases. The trick here, though, is that these are larger. With the same intercell spacing, you're looking at a 14% larger module. Now, a lot of manufacturers are getting around this by really squeezing those intercell margins, let's call them, trying to increase the overall, call it apparent cell sizing in a module without having a similar increase in the size of the module. If you were to not squeeze those cells in tighter, 14% is a pretty significant increase in the overall module size. And we'll see that later when we walk through some of some examples of modules out in the market and how the size does play an important factor in array layouts, in overall weight, etc. And then you see here some of just how truly large an M12 wafer would be. And this doesn't come without drawbacks. Obviously, we spoke about the size factor, but a larger cell with the same material should, in theory, be more susceptible to breakage and microcracking. We know from our friends at REC Group that microcracks are very impactful, let's call it, to the lifespan of a module. They're hard to detect. They're very prevalent. Some of this can be mitigated with just good installation practices and transportation. A lot more of it has to do, though, with wafer technology and wafer size. So let's keep rolling here. Wafer size, where we're headed. So this came from a nice article from PV Magazine earlier this year on, kind of what the predicted mix would be of wafer sizes overall in the market. So you see here in 2012, and I think this is a typo that says 5 foot. I've yet to see any 5 foot wafers, but I think they mean 5-inch wafers. That's going to be basically SunPower technology. And this is the overall kind of global market for modules. So SunPower, obviously a lot larger than this in the United States here, but overall as a percentage of the market, a very small percentage of the market is that 5-inch format. The predominant wafer size here is M2, which remember is 156.75, and then a small percentage of those larger M4 wafers, which are 161 millimeters. So fast forward 2 years to 2020, where are we? We're seeing somewhere still around 20% of the market in that M2 format. Call it almost 60% of the market in that M4 wafer format, and then a small proportion of M6 and larger cells. Looking forward down the road here, we're going to see that M2 basically being obsoleted in favor of M4 and M6 wafers. So this is here to stay. It's not going away. I think the increases in output and in efficiency for some of these manufacturers are just too hard to deny, and this will be a part of our landscape for years to come. Now, the fact that the wafers are getting larger shouldn't really have much impact in the aspect ratio of modules. They still should remain somewhere around a 2-to-1 aspect ratio. So for those of you that like the nice predictable rectangular shape, no changes there. You are going to see the overall dimensions increase, even though manufacturers are again squeezing those intercell margins or the intercell spacing. You will see larger and larger modules come to light, and we will continue to be bombarded by those announcements of 600-watt utility scale modules and 700 watts, and it's going to be really interesting to see kind of the arms race in watt classes continue, and see what manufacturers bring to market. We saw early in 2019 a couple manufacturers toy with the idea of a 66 cell module. I don't know that any of those will really come to market, especially now that you're seeing much larger wafer sizes. It just becomes almost too big of a module for your typical residential installation. But I do think we will begin to see some interesting cell combinations, let's call it, in the utility scale space. So some points to consider. Size matters, but and in theory, a larger module is good for everybody. There's some real practical considerations to make here, though, and the first one obviously is you make the cells larger, you make the module larger, and it just according to plain old physics, it will weigh more. We've been pretty fortunate in this market to see modules continue to be between 39 and 41 pounds. I'm the last guy to say that's an easy module to work your way up onto a roof. I think that will remain a practical consideration for most module manufacturers. I mean, I think that's one of the biggest reasons we don't see 66 or 72 cell modules in the residential space, and that's just that they become too heavy and too impractical to get up onto a roof in a regular fashion. So think about what's the heaviest module you would want to take up a ladder? Well, for me, that's like 20 pounds because I'm lazy. But I think for most of us, we'll continue to see something around that 40-pound paradigm. I tried to look up some numbers from OSHA here. 50 pounds is the maximum one person lift, and I think we've all got our own opinions on how applicable OSHA is to our business. It does remain a very labor-intensive industry in terms of installation, and I just don't see us going much beyond that 40-pound threshold. Another thing that's really interesting to think about is, we've got to get all of these modules out to a job site. Most of us are not using flatbed trucks to do so. So, these things have to go in a box truck or a Sprinter, or just, a plain old pickup. And this is definitely something that has been in the back of my mind as I look at new module technologies and formats and data sheets is, geez, there will come a point, and I don't really want to be there when it happens, but there will come a point where, an installer goes to place the pallet in their pickup truck and it won't fit in between the wheel wells. So I looked up, current model Silverado. 50.5 inches between the wheel wells, which, you know, we're not there yet. But once you add on the, you know, the packaging and the palletization of that, we're getting close to that in a lot of the modules that are out on the market right now. And I think, you know, this may have been behind some of the thinking around vertical stacking rather than horizontal stacking in module pallets. So maybe that's our way around this as an industry, as we, you know, as we entirely consolidate on horizontal stacking, excuse me, in vertical stacking. But it does remain a consideration. And for many, you know, for many installers who are doing, you know, multiple pallets in a vehicle, you know, pallet of modules plus a, you know, 3-4 modules and all the other equipment, you kind of have to wonder, like, at what point will we no longer be able to put two pallets in our box trucks or our, you know, Sprinter vans, and where does that trade-off occur between, yeah, I've got a lot of watts per module, but now I can only fit, you know, 25 of these in my truck. So I'm curious here, and I'd love to hear you guys' comments in the survey of, you know, what kind of vehicles you guys use for jobs? How do you get product out to the job site? You know, have you thought about what fits and at what point things will no longer fit? It's a bit, you know, theoretical of an exercise for me, but for you guys, this is really practical stuff. You know, how do you make decisions on what your fleet vehicles will be moving forward based on trade-offs of, you know, cost and carrying capacity and size? Yeah, it'd be interesting to hear, you know, from you guys in the survey what you use and whether you've thought about this or not. Other points to consider is MLPE, module level power electronics. And, you know, through 2014 and 2017, we're seeing somewhere around 80 to 85% of the market in the United States on either SolarEdge or Enphase, which, you know, is great in terms of functionality and optimization and mitigation of shade, but, you know, more so than string inverters, you really got to think about which equipment pairs with which modules. And, you know, these modules are increasing in efficiency, you know, through a combination of new technology and old physics, let's call it. Some of them are getting higher wattage as, you know, in an equal proportion of voltage and current, and some of these modules are seeing higher wattage just based on higher current alone, which will have impacts on which equipment you're required to use. So let's dig into that a little more. I did hear just a quick MLPE comparison of, you know, a really prevalent module right now, which is the TP2M lineup from REC, something that's on our roadmap for Q1, which is the Longi LR4 black on black 350, and then a module we don't carry, but, you know, we see this somewhat out in the market, which is a Solaria P370. So the most straightforward of these is the REC TP2M. It's pretty standard technology at this point, split cell mono PERC, and you're able to use a P320. Those are phasing out, so, you know, pretty soon here we're going to all be using P340s exclusively, or if you're an Enphase installer, an IQ7. So, you know, pretty cost-effective MLPE. The Longi lineup, however, you know, part of the way that they get to, you know, these higher watt classes, larger cells, more current per cell. So the ISC on these modules eclipses the 10 amp mark, and at this point we're forced to consider a P505 or this is on the roadmap from SolarEdge, a P430 optimizer. So just right there, more expensive in terms of module level power electronics for using that module. Fortunately, on the Enphase side, they have the foresight to rate all of these microinverters as 15 amp capable. So you avoid some of those challenges with Enphase that you have on SolarEdge, which is, you know, pairing the right module to the right optimizer and not strictly looking at the watt class, but the current as well. Solaria, you know, a bit of a different technology, admittedly. You would be able to use the P400. That's phasing out here soon. I believe that will be replaced by a P401. You know, but again, a more expensive optimizer than just the watt class would indicate. And you would be able to use an IQ7 Plus, although you are getting to the upper, you know, call it the upper limits of, you know, its watt class capability. Those have an AC output of 295 volt amps, 295 watts, let's call it. So you know, you're starting to get to the point where you're running a pretty aggressive AC to DC ratio, and I suppose at this point you'd be tempted to think about the IQ7X or the IQ7A. And I say both of those. I'm not super familiar with the Solaria P3 or the Solaria 370 and what the you know, call it the ratio of wattage to voltage to current is there. Takeaway here is that you've got increased MLPE cost, and I purposely didn't publish any numbers here on cost, but you know, obviously the higher up you go in the MLPE hierarchy, the more expensive it's going to be, and you've got to think about, you know, what's my MLPE cost per watt, in addition to the module cents per watt. There's no free lunch, as my mom likes to say. So the next point I want to make here is, you know, comparison of dimensions and power density. And I kind of pick on Solaria here a bit because it is a module that we've seen out in the market for years now, and I've done the comparison for folks on, you know, the size and what that means, and that you know, this has been one of my sayings for a long time is, you know, module watts are not all equivalent, and you really need to look at the module area efficiency. So we've got here the same three modules that I've used for comparisons earlier in this presentation. The REC 320 TP2M black, which is not a black on black, but just a black framed module. So the dimensions here, 39.25 width, and I realize these are all arrayed here in landscape. You know, typically when we're talking about width, we're talking about the narrow side. So 39.25 by 65.94. So one of the shorter ones of the, you know, call it traditional 60 cell formats. This works out to a module area efficiency of 0.123 watts per square inch. The Longi that's coming out in Q1, and this is, you know, admittedly on the lower end of the watt class binning, and I would expect this to, you know, to jump to a 360 in pretty short order once the product is launched, but a bit wider, 41.42 inches. So, you know, already almost 2 full inches wider than the REC 320, and quite a bit longer as well, 69.92 inches. So this shakes out to a module area efficiency of, you know, 0.120 watts per square inch. And, you know, again, some of this it's a bit of an unfair comparison because we're talking about a brand new product for which the bins are going to come out on the low side. If we were to look at, you know, the middle of the normal distribution here, it'd probably be a 360 or a 365, and you might see the same, you know, watts per square inch. The Solaria, on the other hand, is a bit different in terms of, you know, format and aspect ratio. So it's quite a bit wider than your typical 60 cell, 43.94 inches. So you know, call it 4.5 inches wider than the typical REC or, you know, Q cells or any of the other common 60 cell formats, and a bit shorter as well. So 63.82 inches, little over 2 inches shorter than, you know, kind of a typical 66-inch module. So, you know, I think we've all got opinions on aspect ratios and whether they matter. And, you know, your typical homeowner's probably not going to be able to spot the difference between, you know, something that's a pretty clear 2-to-1 aspect ratio and something that's a little more squarish like this. This module works out to 0.132 watts per square inch. So more efficient per square inch than either the REC or the Longi, but we're also comparing, you know, kind of a premium product to what we would call a workhorse or a run rate product. When these comparisons have come up in the past with Solaria, kind of done the math for customers, and it's, this works out to be somewhere around an LG 330 or an LG 335. So, watt class is not everything. You really got to do the math on whether you're actually getting more or not, or, if it's just kind of, funny money, as I would say. So, overall, just looking at the dimensions, it's not a terribly interesting exercise. Glenn wasn't able to join us today, Glenn Hall, who you guys all know from our application engineering team, but he was kind enough to whip together some layouts in AutoCAD so we can see, practically what does this work out on a, called an average roof. So we've got a layout comparison here using the RC320. This is part of a roof here. He took the south-facing portion of the roof. Obviously, there's more house here beyond the peak. It doesn't just drop off a cliff. And on this roof with kind of average setbacks, he was able to arrange 30 panels for a 9.6 kilowatt DC array. So again, kind of a nice tidy layout here. The 2-to-1 aspect ratio, kind of these stack nicely. If you needed to, you could do something really similar in portrait. You could probably mix orientations here if you really wanted to squeeze in, maybe another row along the top. You could do the top row and this row in landscape, and really maximize the output of this roof. Note here, though, in some of these comparisons, 3 full rows of portrait, and we're able to make use of most of this roof valley here along this, this hip. So let's move forward. Let's see what this longy looks like. Here's first example of trade-offs. So, working down from the roof with this 3-foot setback, we're not able to squeeze in this 3rd row of portrait. We did not cherry pick this roof. This is just kind of an unfortunate output. This is an instance where you would most likely be required to do this roof in landscape orientation, and there's nothing wrong with that. I think our predominant racking still is Ultra Rail 40, which is a lot easier to use in portrait orientation and landscape. I think you could fit a similar array size here in landscape orientation. Does become a little trickier and a little more costly to do landscape in with a railed product. Fortunately, we've got railless product that works really well in landscape, but it's a question of what's your organization comfortable with doing? What are your guys used to using? How do your designers like to work as well? So in addition to not being able to squeeze in this 3rd row of portrait, we're also not able to get these last 3 modules here along the roof valley. So pretty unfortunate. Again, we didn't cherry pick this roof. With the same roof, the same setbacks, we're only able to squeeze in 6.65 kW. I think at this point you'd have some options to use a landscape layout, to consider using some of this gable here on the call it the western face. But that comes with costs as well. You're talking about additional conduit supports, possibly another junction box. So the trade-offs here. The last one we'll look at is the Solaria 370. So because these are shorter, this one actually works out, in the homeowner's favor. We were able to squeeze in not the same number of modules as the REC 320, but given that they are 370s, we're able to get even a slightly larger DC array. So I mentioned a few times we didn't cherry pick this design. I would love to have to be honest with you guys, I would love to have had an example in this instance, you're able to fit a larger DC array. Now you could make the same case if we were using landscape orientation for a railless product, let's say, you'd have fewer modules that would fit. So the point here, there's trade-offs. Before you make really impactful decisions on what your sales guys are going to sell and what you're going to install, try to think through all the angles. Think about what will fit, what are common roof sizes and layouts in your area. I think a lot of you guys work in areas of the country where you don't have a lot of gables and valleys and hips, and you've got nice clean east-west or north-south roof orientations. You may be able to be a little bit more creative and a little more aggressive on the sizes of modules you use and the layouts you're able to do. Some of us, like those of us in California, smaller lot sizes, a lot more two-story homes with, call them, really interesting roof layouts. So it's really going to be a question of what's going to work best for your business, and again, considering all the angles of what will fit, what will your MLPE be required to be. I guess the best, most ideal situation is probably something like South Carolina, where there's really large ranch style homes with lots of available roof space that I believe South Carolina is still NEC 2014. So you're doing string layouts. There you're just looking for bang for your buck. So really going to depend on your area, what your code cycle is, what your typical roof looks like. And again, the takeaway is think of these as pixels on a screen. With smaller pixels, you're able to design more. You're able to design I'm struggling to elaborate this point, and I apologize, but with smaller pixels, you're able to design tighter curves, tighter lines, and make more panels fit in a lot of instances where you've got gables and hips and valleys, etc. So lots to consider there. We also talked about how mixed orientations would work with some of these formats. With the REC on the left and the Longi on the right, you're able to mix orientations with really minimal impacts. So not exactly 2-to-1 here, but you're seeing that the 5 portrait and 3 landscape lines up really closely. I don't think Glenn, oh no, he may have. I think he did plan out the inner module spacing there for mid clamps, because I do see some gap there between these modules. On something like a Solaria, it's not going to work out that well because they've got a different shape, and modules come in all shapes and sizes. So lots to think about for what would work best for your business. In terms of our module roadmap and what we're going to be carrying from some of our more common brands, we've got a number of modules in stock right now from REC. Alpha 365. We're going to be bringing in some Alpha Black 360 early in Q1. So really excited to see the black on black Alpha. We've got REC 315 TP2Ms that are winding down, and a small selection of 320 TP2Ms. Those will go fast, so make sure you give us a call. In Q1, what it's going to look like, Alpha 370, and we should be able to stay on that 360 black watt class for some time. Longi is going to see some changes in their modules and formats. So we've currently got a 60 HPH 320. We've got a limited supply of the 72 cell HPH 380. So make sure you give us a call for any of those commercial projects you're trying to get closed out this year. In Q1, we'll see the LR4 lineup really hit the market. So that's going to be using those M6 wafers. And you're going to see much higher output there. So a 360 black on white and a 350 black on black. From our friends at Q-Cells, we've currently got a Duo G7 330. That's our black on white offering, and a Duo Black 315. Q-Cells is kind of right in the middle of navigating this wafer change. The modules coming out of Korea and Malaysia are still using the call it the M2 format. So you're seeing the G5 and the G7 in, anywhere from a 315 to a 330 watt class. We'll be introducing the G6 Plus 335. So that is one of the modules coming out of that US facility in a 335 or even 340 black and white format. And we do hope to continue having the G5 Duo Black 320 into Q1 2021. From our friends at LG, no changes yet to their wafer lineups. So we're just seeing kind of the natural progression of watt classes through both of their lines, the Neon 2 345 in Q4 and the Neon R 370 in Q4, migrating up to a 355 in Q1, and we should be able to stick with that 370 in Q1 as well. So a combination of new technology, new wafer sizes, and then just kind of the natural progression up the bell curve from all of these manufacturers. That brings us to questions. So Jamie, while I turn it over to you for questions, I'd be remiss if I didn't give ourselves a plug here on Express. A lot of new modules. Jamie and I are working pretty much every week to align our module offering on Express to what's been ordered and what's on the shelves. Check us out, see what's there. We've got some deals on modules, and great place to get data sheets, dimensions, warranties, certificates. All that documentation is there for your viewing pleasure. So Jamie, we have any questions come in?
Yeah, thank you, Josh. Once again, if anyone does have any questions that haven't sent them in already, please submit your question through the question section located on your control panel, and we'll try to get through as many as possible. A question came on early from Ed, and Ed was asking if you can talk a little bit about graphene panels.
Unfortunately, Ed, I really can't. It's not something we've dabbled in. We've been, kind of call it purists on module technology. Obviously, we carried multi-crystalline for decades. The TP2 lineup from REC was, basically the last of the multi-crystalline modules we carried, and we're pretty much strictly, mono-PERC split cell, and P-type and N-type distributor. I will take that question and try to look up some answers and get back to you. So, and hopefully I think we've got your email from your registration, and we'll reach out to you on that point.
Yep, we'll definitely do that. And we've got another one coming in from Ken. Which module manufacturers offer the best product warranty?
That's a great question, Ken. So I didn't speak to this too much, but really one of the paradigm shifts we've seen over the last 2 years is more and more module manufacturers offer really solid 25-year warranties kind of across the module. And you see the module warranties and kind of broken down on 3 axes. The first is workmanship. It was really typical when I got into this industry to see a 10 or a 12-year warranty on workmanship, and basically that's guaranteeing against defects in manufacture. The other axis for warranty is output, and it became really common to see a 20 or a 25-year linear output warranty on output. So basically what the manufacturer would do is give you a guaranteed percentage at the end of that 20 or 25-year time frame of 80 or 82 or 84% of the original watt class. And then the last component to a warranty there is labor. So some of us call this a re fee, a remove and replace warranty that's carried. So it's become really popular over the last 3 years from REC, from LG, from Mission, to see a 25-25-25 warranty. A lot of these manufacturers, REC, LG, Mission, they up the workmanship warranty from 12 to 25 years when you register the project. So it's a pretty simple process, on a rainy day, make sure you've got all your projects registered on their website with the modules you used, the quantity, kind of a bare minimum of where the project's located and what you're calling it. But basically, we're seeing these module manufacturers put their money where their mouth is on indemnifying you guys. That's probably too strong a word. In backing you guys up with 25-year workmanship, 25-year power output, and 25-year labor warranty. So great question, and you can find most of that in the individual module sections on our website under AEE Express.
Excellent. I've got another question coming in from Chuck. Since higher temperatures reduce PV output, wouldn't it make sense to have as much white between and around the cells on modules as possible?
Yeah, all of the things being equal, you'd have lots of intercell spacing to try to keep them cool. That being said, I'm not a physicist, and I don't know how much of a factor that is versus the coatings on the glass and some of the other factors that go into module design. We do see some of our more premium module manufacturers with better temperature coefficients, and for folks in extreme climates, it's definitely something to consider when making your module choices. That said, the intercell spacing, it's one of those trade-offs that if you're using larger wafers and you keep the same intercell spacing, well, one, you end up getting more intercell spacing because the cells themselves are larger. So to maintain the same kind of percentage of spacing, the absolute numbers get larger. And it's a trade-off of how much larger can we make the cells without making the module see the same percentage increase. So it's one of those levers that a lot of manufacturers have pulled on to try to squeeze more watts out of a module without increasing the size to the same extent.
Excellent. I've got another question regarding our portfolio. Is AEE Solar looking at adding any modules manufactured in the US to your portfolio?
Yeah, so we've actually got a number of modules that are manufactured in the US that we carry right now. Mission Solar obviously is a brand we all know based there in Texas, that we're proud to carry. The LG 370 Neon R is a module that's manufactured in the US. One of the Q cells modules that we're looking at for Q1, the G6 Plus lineup, is manufactured in the US. So yeah, it's something we look to. It's we're not seeing the US made and as prevalent now. A lot of this came out of jobs that were destined for ARA funding or covered under the Buy America Act. We're seeing less of those jobs, but we're seeing a lot more brands with US supply, US production, and we're proud to carry them. Sure.
Great. And then I got a question from John. So he's asking specifically in the Denver, Colorado area, but I think just in broader terms, are there any companies that you're aware of that recycle or do a good job recycling solar panels? I know he mentions in the Denver, Colorado area, there's a lot of hail damaged panels that they need to remove from roofs.
That's a great question, John, and it's something that I actually posted an article to my LinkedIn profile a few weeks ago that call it reverse logistics for modules is not nearly as robust as it should be. I think there's obviously a huge green element to what we do here of trying to reduce the really impactful effects of climate change. And you know, I think we're all mindful of our supply chains, and there's just not enough emphasis on, you know, what to do with end-of-life modules and how to keep them from, you know, just piling up in landfills. They're big, they're heavy. There's valuable material in there that can be, you know, recycled and should be. Let me do this, John. Let me take your email there, and there is a recycler that I'm familiar with. I don't know how widespread they are and whether they cover the Denver area, but I'll do my best to put you in touch with them, and you know, hopefully they can take care of you.
And I've got one that I think we have time for maybe one or two more. I've got one that comes in from Bill, and for this may sound like kind of a gotcha question, but I think actually it's a good question to talk about, because this helps to clarify the idea of manufactured in the U.S. versus Asia. So his comment and question is, Mission Solar is owned by a Chinese company? ? Yes. And are the cells also from Asia, or are they from the U.S.?
So I've got to clarify that. I'm 95% sure that Mission Solar is owned by a Korean parent company that I believe is called OSI. The wafers do come from Asia, I'm pretty sure. You know, but they're lovingly assembled in San Antonio, Texas. You know, and this is really similar to the questions around, you know, automobile manufacturing. A lot of the, you know, quote unquote American brands are actually assembled in, you know, Mexico and Canada, and a lot of the quote unquote Asian brands are assembled in places like Kentucky and Ohio. So it's not as clear cut as it would seem from some of the names. You know, Hanwha Q-Cells, Korean-owned company, but you know, they're manufacturing in Dalton, Georgia. LG, Korean company that's manufacturing in Alabama. So not as clear cut as it used to be. I will say that I don't believe that there's any U.S. based now that some of the you know, SunPower and legacy REC plants have been idled and shut down. I'm not sure there's any native U.S. Cell manufacturing going on anymore. I think just about all of that has been consolidated in Southeast Asia.
Great. Thanks, Josh, for the clarity on that. I think that's a good point, and there's a lot of questions that come up around that. So I think that's great information. And so, yeah, we're hitting the top of the hour. So if there are any other questions that come through, please feel free to add them into the survey in the comment section, and we will definitely follow up with you. And we will definitely follow up on the question around PV recycling. I see a note came in from Bill mentioning that that he knows of a company that recycles solar panels as well. So I think that'd be some great follow-up information that we can provide to our customers as well. So
yeah.
Josh, thank you so much for your presentation. It was very informative. Any additional comments?
We look forward to working with you guys now and in the future. We plan on having a full lineup of webinars here in Q4, and look forward to seeing you guys then.
Great, agreed. Thank you all for joining us today. And as always, thank you so much for your business, and have a great day.